Hello students. So we have a NEET question from 2025. Consider a water tank shown in the figure. It has one wall at x is equal to L and can be taken in a very wide in the Z direction. When filled with a liquid of surface tension S and density rho, the liquid surface makes an angle theta naught, which is very small with the x-axis at x is equal to L. If yx is the height of the surface, then the equation of yx will be what? So we have a tank whose length is along z axis. Here in this question, here you can see this is x axis, this is y axis, and direction perpendicular to our screen towards us will be z axis. Length of the tank is along z direction, width of the tank is along x direction, and height of the tank is along y direction. Length of the tank, which is along z direction, is very long. We can take that infinitely long. Now they are asking the equation of this curve, which is yx. The height, technically they are asking function of this height as a function of x, yx. Yx is height of the tank as a function of height of the surface of water as a function of x. So we have to find yx. In this question, two concepts will be used. One Laplace equation of surface tension and one radius of curvature. So let's first discuss those two concepts one by one. So first, Laplace equation of surface tension. It says that if we have a surface will always be two-dimensional. So we have a two-dimensional surface like this. Now we have two dimension in this. One curved part is this one and one curved part is this one. One curved part is this one. So we can, whenever we have a curved line, we can draw a radius for that. Radius of that we call radius of curvature. So suppose that when we calculate radius of curvature for this point, it comes here. Suppose that radius of curvature of this curve is here. Now this we call R1. So for this edge, radius of curvature is R1. Now there will be one more radius of curvature for this part too. And suppose that this part is R2. This part is R2. So radius of curvature for this edge is R1. Radius of curvature for this edge is R2. Now if I give you one more surface like here, this time is a straight line. This time this is a straight line. So here for this radius of curvature will be, suppose that R1, but for this straight line radius of curvature will tends to infinity. We all know radius of curvature of a straight line is infinity. So here R2 tends to infinity. R2 tends to infinity. Here R1 and R2 both are finite value and both are different. If both become same, then it will become a surface of sphere. So in a sphere also we have two radius, but both radius are equal. R1 is equal to R2. R1 is equal to R2. Like if you have a sphere, suppose that this is a sphere. So one radius there will be for this circle and one radius there will be for this circle at any this point. So there will be two circular region can be taken there. Like here also one circular region can be taken like this and one circular region can be taken like this. And both these circular region will be perpendicular to each other, and we can also call both these A's will be perpendicular to each other but will not lie in the same plane. So any curved area have two radius. Clear? Now Laplace equation says that if we have a closed curve which have only one surface, like a liquid drop have only one surface, inside water, outside surface. So if we have a closed curve having only one surface made up of liquid whose surface tension is S, then pressure difference in surface tension we all have studied. There is a pressure difference inside and outside liquid bubble or liquid drop. So pressure difference is equal to surface tension S multiplied by 1 by R1 plus 1 by R2. So if we have any closed surface area, closed curve, then excess pressure or pressure difference inside and outside will be S into 1 by R1 plus 1 by R2, where S is the surface tension of the liquid and R1 R2 is radius of curvature in those two dimensions. Now see, if this is not liquid drop, if this is liquid bubble, then we all know pressure delta P will become double, because in that case inside and outside both place will have surface. But in liquid drop we have one surface, in liquid bubble we have two surface. But here we have if you see this question, in this part we have water, only upside we have surface, so no need to take two times, just one time is enough. So this is the first concept that we are going to use in this question. One more concept we have to use from mathematics. Suppose that we have any curve in the xy plane. This is xy plane, and we have any curved surface like this. So here this equation for this curved surface will be written as y as a function of x, y as a function of x. And if we, this is our y, so y will be a function of x, y is equal to yx. Now if at any point we want to calculate radius of curvature, so radius of curvature at any point P will be written as 1 plus dy y dx whole square whole to the power 3/2 divided by d square y means second differentiation of y means this function with respect to x. This is radius of curvature at this point P. This is radius of curvature at this point P. When we'll put the value of dy by dx, d square by dx square, we'll get this value. So these two things we are going to use in this question. First, Laplace equation, pressure difference across any surface is S into 1 by R1 plus 1 by R2. And second concept, radius of curvature at any point is 1 plus dy by dx whole square whole to the power 3/2 divided by d square y by dx square. Now come to question. In this question, the length of the tank is infinite. So when you will take surface of any part of this surface, you will get this structure, this structure. This is along the length of the tank in that question. So this is a straight line. So one radius of curvature for this surface will be infinity, and one radius of curvature can be calculated. So if we call radius of curvature in z dimension will be, I'm not saying z direction, just in z dimension, just for reference. So z direction will be infinity, and radius of curvature in this x direction. Here if we draw any point, then we'll have one. When we say radius of curvature in z dimension, means when our tangent will be along z axis, and when we are saying radius of curvature along x axis or x dimension, it means our tangent will be in x dimension. So when we draw tangent in x dimension, for that when we calculate radius of curvature, it will be this one, 1 plus dy by dx whole square, 1 plus dy by dx whole square whole to the power 3/2 and whole divided by d square y by dx square. Now in this question they have written that theta is very small, and they are saying that take tan theta is equal to sin theta x. Theta will also be a function of x because theta will change. Here theta is more. As you will come close to the center, theta will decrease, and at the center here theta will become 0 2 at this point. If this is the center, theta will become even 0. So theta is also a function of x. So angle, this angle is very small. If we come little close, angle will become even more smaller. So theta is very small. So tan theta is equal to theta very small. So theta square can be taken as 0. It is very small quantity. When we square it, it can become 0. So when you will put here 0, dy by dx is equal to 0, 1 plus 0 square, 1 plus 0 to the power 3/2, it will become 1. So technically in x, for uh, tangent in x dimension, radius of curvature will be equal to 1 divided by d square y by dx square. And one radius of curvature is going to be infinity. Now when we apply Laplace equation, delta P pressure difference will be equal to S, which is surface tension of the liquid, multiplied by 1 by R1. So 1 by r1, 1 by infinity is 0, we all know, plus 1 by r2, r2 is 1 by d square by dx square. So 1 by rx will become d square by dx square. And we all know 1 by infinity is 0, so actually this is going to become ds into d square by dx square. Now at any point here, if this height is y, when we are writing function at this point, we are saying this point is x and y. So this height is y. So from the reference, what will be the pressure difference? We all know if at the depth y, the pressure is rho gh. So this delta p is going to be rho g y is equal to s into d square by dx square. So from this we can write the equation d square by dx square is equal to rho g y by s, rho g y and divided by s, rho g y divided by s. So here which option is correct? Rho g y s into y, or we can write rho g divided by s into y. So our function is, which option is correct? This one is correct. D square y by dx square is equal to rho g y s into y. So here what we have used Laplace equation for surface tension and radius of curvature. One more thing I would like to add here. We all have studied about pressure difference in a sphere. So actually in a sphere, in this Laplace equation, in a sphere, these R1 and R2 will become same. That's why in sphere, delta P, drop, not liquid, in sphere drop, delta P is written as 2 S by R, or sometimes we represent it by T, so 2T by R. Because 1 by r plus 1 by r will become 2 by r. Both radius are equal in sphere. And if this is a liquid bubble, not liquid drop, then this will become 4t by r for two surfaces. I hope this is clear to all of you. Thank you.